All right, hello, hello, hello. Welcome. As you're coming in today, if you could please grab some scratch paper, maybe a calculator. We're going to talk about momentum today. So welcome as we're coming in. We'll give everyone a minute or so, but it's good to be with everyone today. Happy Sunday. I think it's Sunday, right? I feel like my days sometimes get a little confused. So take a moment. We'll wait for everyone to jump on, and then we'll get started. If you're just coming in, hello, welcome. We are doing Unit 4 today, which is Systems of Particles and Linear Momentum. Grab some scratch paper, grab a calculator. We're going to do some problems today. Kristen is here. She's in the chat. Drop a note saying hi to Kristen if you'd like. She is here ready to rock and roll. And as we go through, if you've got questions, I can try and answer them. And also Kristen's a great resource too in the chat. So we'll give everyone just another 20 seconds or so, and then we're going to jump right in to talking about systems of particles and linear momentum. Hello, 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 welcome. If you're just coming in, hello, welcome. We're gonna start in just a moment. And yeah, let's get going. Okay, so lots to do today. We are going to talk about systems of particles and linear momentum. Couple of things, just reminders. As always, we are recording this, and so especially if you are asking questions and you've got your name, make sure that you know that this could be recorded and it might appear in public spaces. As always, also, please definitely, if you haven't followed at Thinkfiveable, that's a great resource for you, especially as the AP tests are coming quicker and quicker. We've got a lot of stuff for you, so go ahead and follow Fiveable if you haven't yet at Thinkfiveable. So today, we are going to talk about really three big ideas. The first one is this idea of impulse and momentum. What are each of these things? How are they related? We are then going to talk for a long time about conservation of momentum. So we're talking everything linear today. So starting in our next CRAM, that's when we start talking about things rotating. But today's our last big day of just like straight linear motion. So we'll talk about linear momentum and collisions. And then at the end, we'll talk about center of mass for a little bit. So let's dive in. So first, impulse and momentum, two key ideas here. The first one is just defining what momentum is, and then how we're going to relate it to impulse with the impulse momentum theorem. So first, what's momentum? What is it? It's got kind of a weird definition. We define it in physics as the quantity of motion, which is, I don't know, it doesn't really make much sense to me, quite honestly. It's just kind of words. The mathematical definition is much more powerful. So if we look on the slide here, we've got P. P is our symbol for momentum, and it is going to be equal to m times v. Remember that m stands for mass and v stands for velocity. We also notice that both P and V have arrows over them, which means that they're vectors, right? So we have to care about the direction when we're talking about momentum. Our units for momentum are kilograms, meters per second. That should make sense if we think about kilogram as mass and meters per second as velocity. So put them together, that's your unit for momentum. And the way that we change something's momentum is by exerting force, having forces that cause changes in momentum. So if a force acts on a particle, it's going to change the particle's momentum. If we think about that, relating it back to Newton's second law, that should make sense to us because we know that forces cause acceleration, and acceleration is changing velocity. So if we're changing velocity, we also have to change the momentum. So everything is connected as we look through these different ideas. But this is kind of one more tool in your toolkit here when we're talking about forces, because we know that forces are going to be equal to the change in momentum over time. So this F equals dp dt is going to be a formula. It's on your equation sheet. I pulled it off of there, and it's going to be an important one as we start to kind of build a bigger picture of all of the different physics ideas and how they connect. Great. So Even more specifically, we'll talk about impulse and momentum together. So impulse we symbolize with a capital J, which is kind of weird, but that's what it is. And it's the name, it's just a label, it's a vocab word that we give to the idea that forces happen over time. And depending on how much force and how long that force is acting, we're going to have a different impulse. And we're also going to know that that impulse relates to momentum. So we need to give a name to this idea of like, if we exert force for a longer period of time, more is going to happen than if it's a quick period of time. And the name we give it is impulse. So you can see impulse, we can calculate it by integrating the force with respect to time. And that's really, a theorem that we can use whenever we're talking about forces and times and momentums, because the impulse is going to be equal to the change in momentum. So we can see at this bottom, this one is a big one. This is the impulse momentum theorem. We can relate force and time and change in momentum through thinking about impulse. So all of these things are equal. And that's going to be a really useful relationship as we move forward. I put a graph on here on purpose. A lot of times that we are talking about this, we have some sort of force function, and we can do some calculus with it, definitely, and do kind of like just like the numbers part. But we also can look at it in terms of a graph. So if we look at the graph on the right-hand part of the slide, if we've got a force time graph, we know that when we integrate something, what we're doing is we're finding the area under the curve. And so if you've got something that's geometric like this, where it's not, not, I say squiggly, that's a funny word, but it's a function that you can use some geometry to figure out the area, we can find the impulse by just doing that geometry instead of having to go through the calculus as well. So that's just a note. We'll do an example problem with that in a couple minutes. So if we have a force time graph and we look at that area under the curve, that will give us the impulse, which we know is equal to the change in momentum. I also wanted to just point out, I always think of impulse, and the way that I remember what it is I think of water balloon tosses. So I don't know if anyone has done that before, but it's like a pretty nice, fun little activity for the summer. I'm coming at you from Boston, and it's nice out, so I'm especially thinking about, summer stuff coming up. But in a water balloon toss, what you do is you've got a partner, and you line up, and you try and toss the water balloon, and you get further and further back from each other. So it's a bigger distance, so it's harder to keep it without the water balloon breaking. And when you try and catch the water balloon, typically the way that you do it is you try to catch it like softly, and you move your hands kind of as you're catching it to minimize the force of the impact in order to keep that water balloon intact. And that's what this is. So if we think about impulse as force over time, if we need to change the water balloon's momentum, right? Because we need to catch it, we need to stop it. And if we extend the time over which we are changing that momentum, we decrease the force. And so when we think of impulse, it's that relationship between force and time. So that's kind of one thing that I always remember impulse when I think of water balloon tosses. So hopefully that is a helpful little reminder. Okay, we're gonna do a couple practice problems with this. So here is the first one. I'm gonna open up a poll. So take a second and think about it, and then see if you know the answer. So I'm going to open up a poll. The question says, identical net forces act for the same length of time on two different spherical masses. Which of the following describes the change in linear momentum of the smaller mass compared to the larger mass? So let me open that up. I'll give you 30 seconds or so to see what you can do with that. This question comes from the 2012 released public practice exam. So take a guess at that. Give you a moment to choose your answer. Great. We've got a couple of folks voting. Take another, I don't know, 10 seconds. All right, if you're going to take a vote, vote now. I'm going to close it. Great. Y'all are crushing it already. Let me show you. We got it right. Good work. Go team. So let's talk about it just to do some due diligence here. But good work, everyone here. We got it right. So let's talk about it. So you all know that the problem here says identical net force in the same length of time. Those are two things that are going to cue that the change in momentum is going to be the same, right? So if we've got the same force and we've got the same time, then the total impulse has to be the same, because we know that the impulse is equal to the force if we integrate the force with respect to time. And if the impulse is the same, then the change in momentum also has to be the same. So this is an impulse momentum question, and it's really more of a just like got to read carefully and pull out the important info to be able to answer it conceptually. Let's see if we can do a little bit less conceptual. We do have to do a little bit of math with this one. See what we can get. So it says a ball of mass m vertically hits the floor with the speed vi, rebounds with the speed of vf. What's the magnitude of the impulse exerted on the ball by the floor? So I'll open up another one. Open up another poll, see what we can get here. I'll give you a moment to work on it. This is another impulse momentum theory question. I will warn you to be careful with your signs. Remember that velocity is a vector. That's going to be important as we look through this one. I'll give you 30 seconds or so to see what you can come up with. Great, got some votes coming in. You're still working, keep going. Take another 10 seconds. All right, if you're gonna vote, now's your last chance. Okay. Great. So if we, someone got it in just under the wire. Nice. Great. So if we look at this one, again, y'all are crushing it. So I'll go over it, but again, we feel like we're in really good shape here. Good work. Correct response is C. So if we take a look at this one, there we go. If we look at this one, we can kind of break it apart first and just, if we're unsure, for a good first strategy is always to just write down what we know, right? So I drew a little bit of a little picture there, just with my ball and the velocity vectors, just to kind of get an idea of what's going on, and thinking about the relationships we can use as we go through. So this one definitely, it asks about impulse, so we know that we want that impulse equals change in momentum. So from there, we just need to plug in and find the change in momentum. This question gets a little weird because your initial velocity is negative because it's going towards the floor, right? So the math gets a little funky, and we've got to make that double negative into a positive. But really, this is a pretty, just once we get our setup correct, we plug it in, we simplify, and we get our answer. Reminder, always, if you've got questions, stick them in the chat. Kristen's here with us, and is just like ready to go to answer your questions if you've got them as we go. Okay, here's another one. I promised you a force time graph, so here it is. we've got a graph showing the force of an object of mass m as a function of time for the time interval 0 to 4. What's the change in momentum? So I'll open up another poll here, and we can see if we can get this one too. Take about 30 seconds here. Great. Okay. I think all of our votes are in. So great. So let's look at it. Again, you all are. You guys got it. We've got this idea. Great. So if we were to look at it, just to talk it out, two things we could do. We're looking for total change in momentum. So we know that's going to be equal to the impulse. So we need to find the area under the curve. Easiest thing to do is just look at it, right? And see that the top, the 0 to 2 second area is equivalent to the 2 to 4 second area. And because it's the second one is in under the 0 in the negative direction, those two are going to cancel out. So your final answer is 0. We can also calculate it. So this is geometric, so we could find the area of each of the rectangles and then figure out that the total change in momentum is going to be 0. So good work here. Great. So this is kind of it's another one, and I put it in here because it's kind of like a weird one. This comes from a practice exam, and I feel like these pop up kind of randomly. And if you don't know how to figure this question like this out, it could get a little tricky. So I wanted to talk about it. So let me open up a poll and give you a chance to answer, and then I'm going to talk through this one. So if you're like, this is weird, Sam, what is this? Just give me a second, see what you can do with it, and I'm going to talk about it in a second. Because this is one that if you don't know how to approach it, it's kind of a weird question. Great. Take maybe 15 seconds. All right, last chance if you're voting. Okay, so for this one, the correct answer here is D. Some of us got that. And the way that we figure this out, there's a couple different ways you could do it. We know that our unit for momentum is kilograms times meters per second. But we also know that change in momentum is equal to impulse. So correct answer is D, because our units for impulse are Newton seconds. And those two, impulse is equal to change in momentum, so that those two units must be equivalent. Different way to do it. If you're like, I don't know, that's weird, I don't really get that. We know that newtons, the unit Newton is something called a derived unit, right? It's a new name that we give to our kind of a combination of standard units. And we know that newtons are equal to kilograms times meters per second squared because of Newton's second law, right? Because we know that force, which is newtons, is equal to the mass times the acceleration. So kilograms meters per second squared. So then if we're like, okay, well, if I know a Newton is a kilogram meters per second squared, and I want a momentum unit, I better multiply that times seconds, so that way we end up with kilograms meters per second. So a couple ways to do that. If we run across one of these on the test, it's really just about kind of like using your formulas and figuring out what the units for each of those different parts of the formula is and see if we can't just kind of like cancel out some things or plug in different versions of it until we can get the one we're looking for. So yeah, I threw that one in there just because I feel like it does pop up, and it's kind of, if you don't know how to go about answering it, it's kind of a weird one to figure out. Great. Okay, so we are going to shift a little bit and look at some free response. So this free response question, we're going to do some of it now, and then we're going to talk about some more concepts, and then we're going to come back to it because later parts of the question relate to the later parts of the content. So first thing is we've got a lot of info here. We've got 2 carts, horizontal level track, no friction. We know some masses. We know some velocities. We've got a spring constant. We've got a force function. We've got a graph. There's a lot of stuff, right? So we're going to just take it part by part and just talk through each part and figure out, what pieces of the setup we need for each part. So the first part asks us at the bottom here, using integral calculus, calculate the total impulse delivered to cart 1 during the collision. So this is the first part, and it hopefully should be something familiar. So as we're going through this free response, I think it can be, as we're doing more of these CRAMs, I'm thinking that as we kind of dive more deeply into it, being able to calculate the whole thing in the amount of, we only have an hour, may not always be super reasonable. And so for this one, instead of going through and calculating it, which if you're already working on it, great, the poll question is just going to ask what relationship did you use or should we use to find it. So I'm going to open up that poll and just think about like what formula or what relationship, what like guiding principle would you use to answer the question? And then I will definitely walk through how to answer it and like step by step do all the math with you. But take a second and see if you can't just answer, in what direction would you go if you were going to start approaching this problem. You can see your options here are, initial momentum is equal to final momentum, impulse is equal to FDT, initial energy equals final energy, or Newton's second law. Take another, 10 seconds. Great, yeah. Okay, good, we got it. So y'all got it. Definitely we need to use impulse momentum theorem. So if we were to actually do it, this is what it looks like. Again, I always like to start with just what do we know? And in this, like I said, there's like a ton of stuff in that setup, right? But just pulling out some pieces here. We know some velocities, we know some masses, we know we've got a force function, we know the collision is 0.16 seconds from the graph, and we know we need to use impulse momentum. So you can see here, all I did is I plugged in the force function for F in our J equals FDT formula, plugged in the force function they gave us, and then I integrated from 0 to 0.16. Now, I think that 0 to 0.16 is probably the part that is a little bit like harder to figure out. The reason I did that is because we see in this graph here that the collision, this is the graph of the collision, right? This is the graph of the collision, and we can see that the end of the collision is at 0.16. That's where the graph stops, right? So the time of the collision is 0.16. We're basically finding the area under this curve. So then all I did was integrated, right? So got an answer, integrated, and then plugged in 0.16 and 0 and solved for my impulse as negative 2.03 Newton seconds. Again, reminder, if you have questions, definitely stick them in the chat. Okay, Cool. I also like to show you always the scoring guideline, right? So this is the scoring guideline that went with this question. You got 1 point for just using the proper formula and plugging in. You got 1 point for actually integrating and then using the correct 0 to 0.16. And then lastly, for a correct answer here, right? Cool. Okay, so let's do B now. So B says two things. First one, calculate the speed of cart 1 after the collision, and then in which direction. So we're going to do something similar here. For calculate the speed of cart 1 after the collision, again, just thinking, what relationship would you use to figure that out? So I'll open up a poll. Think about just like what formula, what relationship, what big guiding idea would you use to figure it out? Take like 20 seconds or so. How would you start? What direction would you go to figure out that speed? Okay. All right, I think we've got some votes, and this time we're a little split, so that's great. That means that we are here for a good reason. So the correct answer is, again, using impulse momentum. So we have the impulse now, right, from the first part. And so now what we need to do is we need to use it and use the change of momentum to figure out the answer. So I think you could... well, let's do it this way, and then I'll show you the answer, the scoring guideline. So for cart 1, we're looking at cart 1, so we know an initial speed, and we know the mass of the cart, and we know the impulse. So the easiest thing to do here is just to look at the change in momentum of cart 1, because we've got a bunch of initial info about it to be able to find the speed of the cart after the collision. So all I did is plugged in my impulse that I got from A. I plugged in my masses and then my initial speed of the cart. And then here for just its math, right? And got the speed of my cart to be negative 1.06 meters per second. Okay, and then B I just showed you. So the second question asks, in which direction does the cart move after the collision? The correct answer there is left. And the reason we know that is because VF is negative, right? So if it's negative, negative usually means left. So, and we know that it starts off going to the right based on the picture, and we made that positive, right? So left has to be negative, and so it's moving to the left. Great. Here is the scoring guideline again, plugging into impulse momentum, getting an answer, and then you get a point for saying left. Okay, cool. So if you have questions about that, oh, okay, good. Thanks for adding that to the chat. I'm glad that's okay. So let's move on to the next chunk of content here, and then we'll circle back to that Frey response question. So we need to talk about conservation of momentum. So 3 big ideas here. First one is just, what is conservation of momentum? How does it work? And I'll give you some kind of tips and tricks for solving problems that have to do with conservation of momentum. We need to talk about collisions. And then we're going to briefly just touch on 2-dimensional collisions. Those don't come up as much. So I really want to make sure that we prioritize just 1-dimensional collisions, because that's where the majority of everything will be. But I do want to at least mention it so that we know what to do. Okay, so law of conservation of momentum is both very straightforward, but also like so important and applicable in lots of different ways that I wanted to say it a bunch of different ways. So the kind of more technical, textbooky way to describe law of conservation of momentum is, in an isolated system with no non-conservative forces, momentum is always conserved. All that means is that assuming that there's no non-conservative forces, so there's no friction, there's no air resistance, things like that, then momentum is going to be conserved within the system. The total momentum remains constant. And then you can see the other way to write it is just initial momentum is equal to final momentum. I'm a big fan of The Office, so this is meant to be funny. Hopefully, if you've seen it, then you get it. It says here, corporate needs you to find the differences between this picture and this picture. And Pam is saying they're the same picture, right? Because the initial momentum and the final momentum are always equal. It's constant. They're the same. I can't think of any other ways to say it, but that needs to be a really like default. Anytime we're asking about momentum, unless there's friction, momentum's the same. Always, always, always. So there's a lot of fun applications to conservation of momentum. The image on the left is something called a Newton's cradle. If you've never seen it before, it's just like kind of a tchotchke. It's just kind of like a round. People have it on their desks. I've got one in my classroom. And it works because of conservation of momentum. So if we look at it, as each of the end balls are hitting the central part, that momentum needs to be conserved. So when the force impacts those center balls, that momentum travels through, and the one on the other side has to move, and then they just go back and forth. This idea also is shown on the two images to the right. So I wanted to talk about them because this is a different application of conservation of momentum, because what's happening here, I like to think of it almost like an explosion. A lot of times we talk about this sort of thing in terms of explosions. The two people are starting, in this top right picture here, are starting at rest together, and then they're pushing each other apart. In this scenario, momentum is definitely conserved. They start with 0 momentum, and their total momentum after they push each other apart is still 0, because the velocities are vectors, right? They're going in opposite directions, and the total momentum is 0. We can see it especially when we compare it to the bottom image here. Now that there's 2 people on the right-hand side, you can see that they don't move as fast. What's happening is their mass is increased, right? So because their mass is increased, when they all kind of explode out, they're not going to move as fast. Their velocity will be smaller because momentum needs to be conserved. This is also just funny. I found it as I was looking for examples to show you, and I thought it was humorous. So there is that. Looks like a Newton's cradle, right? Okay, so one problem-solving strategy here with conservation of momentum is to create a table. So this is just kind of a very general, generic example of a situation where momentum is conserved. We'll talk more about collisions in a second. You've got 2 pool balls, one going towards the right, one going towards the left. They collide, and then they break apart after the collision. One way that we can approach these problems is by making something called a momentum table. So we know that the total momentum is always going to be the same, right? So what we can do is we can add up the momentum of each of the objects before. So here I've just got kind of a general generic expression for this first object here beforehand. And then same thing, object B here, same general generic expression for B. We add those up to get a total. And then we know that this total in this box has to be the same as this one. So we can work backwards depending on what you're looking for in terms of like masses or velocities or whatever, by making sure that these 2 totals are always the same. So this is kind of just one way to bookkeep, to kind of keep track of all of your different momentum values, because it can get a little complex as you go. So it is just kind of like a different way to keep track of your work, if that's something that's helpful. Let's talk about collisions. So there's 2.5 types of collisions. I say 2.5 because there's elastic collisions, there's inelastic collisions, and there's like a special case inelastic collision. So let's talk about elastic versus inelastic first. Elastic collisions are defined as collisions where the total kinetic energy of the system is conserved. So typically, when we talk about elastic collisions, in like reality, really the only time that happens is subatomically, right? So subatomic particles can collide elastically. In the regular world, macroscopically, that doesn't happen, but we do that thing in physics where we're like, yeah, there's also, we also say there's no friction all the time, and there is. So we can do the thing where we're like, assume an elastic collision has occurred. And when that happens, as soon as you see elastic collision, that needs to cue you to be like, yep, elastic collision, total kinetic energy is conserved. That's, the way of the question to tell you about the kinetic energy is to say that it's an elastic collision. The other type are inelastic collisions. And so these are when the kinetic energy is not conserved. And as I say here, in real life, pretty much all of your collisions are going to be inelastic because you're going to lose energy to like heat and sound, and sometimes there's fire or, whatever. But the idea behind an inelastic collision is that the total kinetic energy is not conserved. And then there's this like special case of inelastic. Still, kinetic energy is not conserved, but the difference is that in a perfectly inelastic collision, the objects stick together. So I think of this like a football tackle. You can see the two football players come towards each other, and then as the guy's getting tackled, they're stuck together. So that's always how I kind of remember perfectly inelastic. So there's like pool billiards balls, and then there's football player tackles, and then there's like everything in between. But the two kind of takeaways here are you see elastic collisions, total kinetic energy is conserved, and then perfectly inelastic means the objects stick together. Okay. Cool. So let's do some practice. So object moving on a horizontal frictionless surface makes a glancing collision with another object initially at rest. So in this case, which of the following is true about momentum and kinetic energy? So I will open up a poll, take a second and think about that one, and we will go from there. Take like 30 seconds or so, I think, for this one. So we're thinking, as we're looking at this one, we're thinking about what we were just talking about with the collisions, and also my very long rambling about how momentum is always conserved. Hint, big hint. I kind of just gave it away. Yeah, good. Okay, I think we got everyone. Great. So y'all got that one. Good work. We got this. So momentum is always going to be conserved, right? It says frictionless, so we know that there's nothing, no forces taking away momentum. So momentum is always going to be conserved. And then because we don't know enough about the collision, glancing collision sounds like it's something, but it's really just like, it's telling you how they're colliding, but it doesn't really tell you anything about the energy. So kinetic energy might be conserved, but it might not. We don't actually have enough info to tell. So the answer is A, momentum is always conserved. Kinetic energy may be conserved. Okay, yeah, so this is me just continuing to harp on this, right? So no matter what type of collision is happening, momentum is conserved. It just is, always. And there's another funny cartoon. This is another kind of like, it's an explosion joke, right? Because as one fish was propelled from his sneeze, the other one has to go in the opposite direction to conserve momentum. Great. So here's just a couple visuals. Again, more ways to talk about the different types of collisions and kind of just like ways to help you picture it. So elastic collisions are like pool balls. They're gonna collide and they're gonna break apart. Perfectly inelastic. Another very common example is like trains, because when trains collide, sometimes they stick together, right? And then they're both moving at the same speed, stuck together in the bottom right part of this picture. Okay, here's another one. So we've got a railroad car, mass 1,500 kilograms, rolls to the right at 4 meters per second, collides with another railroad car, mass is 3,000 kilograms, rolling to the left. The cars stick together, and then their speed immediately after the collision is. So this is a conservation of momentum question. I'll open up a poll. This is one that if you think the momentum table will help you, this is a great opportunity to practice that. So take a couple moments to see if we can get an answer for this. And I will open up the poll. Great. Great. Take another 20 seconds or so. We've got some votes in. All right, if you are gonna take a stab at it. Yep. Okay, cool. I think we've got everyone. Y'all are crushing it. I'm so excited for you. Great. So we got that one right. Great. Good work, team. So we will talk about it just briefly. So first, always, if we're unsure of where to start, we should write down what we know, right? So I've got my list here. I've got masses. I've got velocities. Notice that I made the velocity, the initial velocity for the second car negative because it told me that it was going to the left, and I know that they stick together. So I set up a momentum table just to show you how you would use one of these if that's something you want to do. And what I did is I said, okay, my first railroad car, what was its momentum? My second one, what was its momentum? And then I found my total momentum initially. And then I know that because momentum's conserved, that's got to be equal to my momentum after the collision. So I've got this negative 3,000 would be kilograms meters per second, right? And we know that the momentum after the collision has to be this. So then from there, from there, all I need to do is figure out the speed. They're stuck together, so I added their masses and found the speed of the two cars stuck together after the collision. The question also, this is just a note, question asks for speed. So it's actually, if you solve for the velocity, it's negative 2/3 meters per second, but the question asks for speed, so we can ignore the negative. Great. Okay, so we're back to this question. So I, again, am picking the same question when we're looking at all the different parts just to show you like how much you know and how like, I know we think about free response questions sometimes and we're like, this is intimidating. It's a lot of like A, B, C, D, 1, 2, 3, there's a lot of parts and you think like, oh, I've got to combine all of my different topics together. And that's not always true. So this one came from just a couple years ago. And this is all momentum. It's just asking about momentum in different ways in different parts. So if we were to look at C, the first part asks you to calculate the speed of the cart 2 after the collision. So again, I'll show you all the work here, but let's just start by thinking about what relationship should we use if we're going to answer that question. So I'm going to open up the poll. We've got conservation of momentum, impulse momentum, conservation of energy, or Newton's second law. What direction do you think you would go? Where would you start? Take another 10 seconds or so to think about it. Okay. Okay, so we've got some folks saying conservation of momentum. Actually, there were multiple answers here. We could do conservation of momentum. You actually could also use impulse momentum to figure this one out. I did conservation of momentum just because it fit nicely with this section, but either one works. And we're going to do just like what we did in the multiple choice that we just looked at. So setting up your momentum table, finding your momentum of each of the carts before the collision, knowing that the momentum's conserved, and then looking for what the question's asking you for, which in this case is the velocity of the second cart. So we can set it up here. I used P equals M times V, right, to get those different individual momentums, and then set my total initial momentum equal to an expression for my final momentum, plugged in my masses and my velocities, and got, I think it's that's a hard dot to see, but it's 1.93 meters per second. And then B, or part 2 here says, show that the collision between the two cars is elastic. So that's kind of a weird question. You're like, what does that word show mean? On the test, basically what it's saying is like, assume that the collision is elastic. Do the math that proves that it's elastic. And the way that we do that for this is we say, okay, so if it's elastic, if the collision is elastic, then I know that the kinetic energy before the collision must be the same as the kinetic energy after the collision. That's the definition of an elastic collision, right? So if I can figure out my kinetic energy before the collision and my kinetic energy after the collision, and they should be the same. If they're the same, then the collision's elastic. So here it is. Same deal. We know a bunch of stuff now. We know initial velocities, we know final velocities, we know masses, and then remembering that the formula for kinetic energy is 1/2 mv squared, and all we did here is just found my initial kinetic energy for each of the carts, my final kinetic energy for each of the carts, set them equal to each other, and we see that we get pretty much the same number. The only difference is there's like some rounding that's going on, which is why, it's not exact. This right side just has some rounding because those numbers are a little weirder. Cool. So here, again, showing you solutions. So I picked, you can see for the first one, this was an alternate solution. There were 2 solutions listed, either using impulse momentum or conservation of momentum. I chose conservation of momentum, so I'm showing you this one. Just using it, knowing that you needed to use it, get to a point already, but without you even actually plugging anything in, just showing that you're like, yeah, I have to use conservation of momentum, earned you a point, and then plugging in and getting an answer. For the second part, showing the collision's elastic, again, just like knowing that the kinetic energies must be equal. So just like knowing the physics, even if you don't actually do all of the stuff right, just knowing that that's what you're looking for is huge, because that would earn you another point in this problem. And then actually substituting and getting an answer is the second one. Okay, quickly on 2D collisions, just because I want to make sure we have enough time to talk about center of mass. For 2D collisions, We just need to know that momentum is conserved independently in each of the dimensions. So total momentum has to be the same in the x, and then total momentum in the y has to be the same, and then if there's a z, there's not usually a z, but the total momentum in the x doesn't have to be the same as in the y. They can be different, but before and after in each dimension has to be the same. If you were to have to solve for something, you would want to make a separate momentum table for each dimension, just like in like projectile motion or something like that. We know that x and y are always going to be independent from each other. And then lastly, finding the components of each of the velocity vectors. So something like this, it gives you some velocities at an angle. We would have to find the x component and then the y component for each of the velocities in order to find the momentums. Cool. So here's a practice. We're not going to do a poll just because of time, but if we look at this, got an object, got an initial momentum that looks like this arrow, this vector, strikes an object initially at rest. Which of the following sets of vectors may represent the momentum of the two objects after the collision? So this is a conservation of momentum question. We know that the final vector between the two objects has to add to look like this. That's how we figure it out. So if we look at A, we see that those two are going to cancel each other out. That's not right. We need it to look like this top vector, right? So it's not A. B is going to be, if we do head-to-tail method here, B is just going to be a very, very large, too large vector. It's pointing in the right direction, but it's going to be too big. So it's not B. C actually will end up, if we do head-to-tail method, C is going to have a vector pointing left, which is not correct. So that's wrong. It must be D or E. And then if we think about adding these two vectors up head to tail, then we can see that E must be the correct answer. Because if we think about what that will look like, what if we added those two up and drew our resultant vector, it will look like this. Cool. Okay, center of mass. 8 minutes, we can do it. So for center of mass, 2 types of ways to figure it out. The first one is by inspection. So that's just a fancy way of saying looking at it and figuring it out and knowing some rules about center of mass. The second one is calculating it. And we can calculate it either just like algebraically, or sometimes we need to use calculus. And I'll show you both options. This is not as the idea of objects having a center of mass is important because all the physics we do is assuming that we're doing it at the object center of mass, but the actual like being able to calculate center of mass is like sometimes maybe 1 or 2 questions on the test. So this is definitely, you know, if we're prioritizing conservation of momentum, impulse momentum, those are much more important topics. But this does come up, so I wanted to include it and talk about it for just a couple moments. So first, what is it? In physics, we simplify because when we're talking about, you know, real macroscopic objects, they're extended beyond just one point in space. So we need to simplify them in order to do physics. And the way that we simplify them is we can find one point of an object that acts as if its entire mass is concentrated at that single point. And we can do it mathematically. That point is called the center of mass. We symbolize it with an x sub cm. And the easiest way to do it is by inspection. So if it's something symmetrical, so you can see this is a triangle, it's a circle, it's a square, the center of mass is just going to be its geometric center. So if we look at it, we can just kind of, you know, eyeball where the center of it is. And we treat that as the center of mass. There's a little note down here. Sometimes you see center of gravity, assuming that we're in a uniform gravitational field, like on Earth, it functions, it's at the same point as the center of mass. It's defined as just the spot where gravity acts on the object. Again, this is like, that's in your list of priorities, not that important. Okay, so we can look at it by inspection. The other way we can do it is we can calculate it. So if you've got something with multiple points, so if you've got like, I don't know, 3 particles, and we want to find the center of mass of those 3 particles, this formula is on your equation sheet, And all we do is we sum up the mass of the particle times the position of the particle, sum all those up, and then divide it by the total mass to find the center of mass. You'll also sometimes see it's usually called a thin rod of non-uniform density, which basically means it's an object that's got some length, but the density of it isn't the same. So we can't just look at it to figure out where it is because the mass on one end is different than the mass on the other. If that's the case, we can integrate. This is not something on your equation sheet. I just like to point that out. But if we integrate the position with respect to mass and divide by total mass. So it's basically doing this, but it's the calculus version if it's a continuous object instead of just like a couple different points. I also have a note down here. If we've got something that's irregular, a third way to do it is figuring it out by suspension. So if you suspend the object from 2 or more points, the center of mass will always be located kind of on the line of which it's suspended. So we can kind of, if we do it by a couple different points, you can kind of like figure out where it is by process of elimination. So center of mass, if we've got 2 points, I've got this here. All we need to do, like I said, is do the mass of the object times the position on the axis, add all those up, divide by the total mass, and get a position for the center of mass. So that's how we use this formula here. The sigma, the sums are, don't let them confuse you. All it means is take each of the masses, the m1 times x1 plus the m2 times x2 plus however many you have, and divide it by the total mass. And then this one, again, we're not going to spend too much time on it, but if you want to like go back to this video and pause it and really dig into it, this is how we would figure out the center of mass of something that's not uniform. So we've got a density expression, kx. We know the length, we know the mass. We're going to use this formula to integrate. And we know the definition of density is mass over position, right? So the dm dx here, and then this is just a bunch of calculus. Like it's not actually, honestly, I don't even find it very particularly interesting. It's just some calculus to figure out an expression for where the center of mass of this object is. Cool. So lastly, again, we're not going to pull here just because of time, but I do want to just talk through this because sometimes we're going to see this word center of mass and get confused, and I don't want you to. So we've got this problem, 2 people initially standing still on frictionless ice. So this is an explosion problem, right? They push on each other so that one person moves to the left, the other person moves to the right. What's the velocity of their center of mass? So I feel like when I always look at problems like this, I'm like, oh no, like there's so many different velocities. How do I find the center of mass? And it's moving and their positions are moving and what's going on. But really, this is not as hard as it looks. If we think about it in terms of momentum, if they are initially standing still on frictionless ice next to each other, their center of mass is going to be in the middle. And then because momentum is conserved, if they're initially standing still, their initial momentum is 0, which means that their final momentum also has to be 0, which means there's no change in momentum. So the velocity of their center of mass is 0. So just because it says center of mass doesn't mean that it's asking you to do any of those like sigma, m1, x1, like none of that. All it's asking is the mass, the center of mass between them, is it moving? And the answer is no, because this is a conservation of momentum problem. This is not like a crazy calculate the center of mass problem. And so I wanted to point that out because pretty much unless it's like explicitly being like calculate the center of mass between these 3 particles or whatever, you don't really need to do those formulas. It's even though the problem is using the word center of mass, it's not usually asking you to do any sort of calculating using those formulas. It's asking you about a different concept. And a lot of times that concept is going to be momentum. So that's that. Okay, so just to wrap up really fast, this is a nice summary slide that Kristen sent me. Law of conservation of momentum. Initial momentum is equal to the final momentum. We've got 3 different types of collisions. I drew them out for you so you kind of know what they look like. We know that momentum is always conserved, always, 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 and that kinetic energy is sometimes conserved, sometimes not conserved, depends on the collision. So, last tips, momentum is conserved, count on it, back pocket it, like pretty much always, unless there's friction, momentum is conserved. It's really important, right? It's just a rule. It's really important. When in doubt, draw a diagram, list what you know, what you're looking for, and then, as always, take a deep breath because we can do it. So if you have questions, definitely stick them in the chat. I'll stick around just for a moment, but otherwise, thank you so much. Kristen is going to hop over to Discord in a second. We've got some upcoming events. So tomorrow is trivia, momentum trivia on this. So 9:30 Eastern time. And then our next CRAM is going to be kind of a combination of a couple different things. We haven't talked about circular motion yet, so we'll talk about that. Uniform circular motion. And then we're going to start talking about some rotational topics. The next 2 CRAMs are going to be rotational stuff. So we'll talk about the first half in this next CRAM, and then the rest of the rotation content in the following CRAM. And it's going to be Tuesday the 30th at 6 Eastern. So yeah, so Kristen will be in Discord. Definitely hop over there. Keep this convo going. If you have questions, she is awesome and can definitely help you get all of your questions answered, or if you just want to chat about physics, she's pretty great. So head over there if you'd like. Thank you for being here, and I'll see you next time.